Number 31. Consider two cylinders that start down identical inclines from rest, except that one is frictionless. Thus, one cylinder rolls without slipping, while the other slides frictionlessly without rolling. They both travel a short distance at the bottom and then start up another incline. Letter A. Show that they both reach the same height on the other incline, and that this height is equal to their original height. All right, so so here's a little diagram right there. There's some incline here, some incline here. The two inclines might be the same, they might be different. I just chose to show them as both theta. You could have done theta 1 and theta 2. It doesn't really matter. Because we're just going to be looking at this from an energy perspective. Okay, remember, when there's not a lot of information given in terms of numbers, most likely you're going to be using energy considerations to answer your question. So I'm going to look at the red one first. Okay, the red cylinder, and I'm going to assume that the red cylinder is the one where there is no friction. Okay, meaning it's just going to simply slide down the hill. Okay, it's just going to simply slide. It's not rolling at all. It's just going to slide down the hill, and it continues to slide all the way on up to its final position. Okay, and what we just have to show is that the height here, h, is equal to the height over here, h. Now you might say, well, that's quite apparent, but why don't we think about this in three separate stages? Okay, we'll call this part of the problem on the left-hand side stage number 1. That's basically the initial point where everything is at rest. Okay, stage number 2 is now going to be the part in the middle. All right, and this part is where the kinetic energy of both systems are at their max. Okay, and then number 3 is we are now again at rest, and it's basically all potential energy at that point, right? Because it has some height relative to the ground, and if it's at rest, we know that there's no kinetic energy. Also initially then at point number 1, it's also all potential energy. Okay, so now for the red cylinder, okay, so this is for letter A, this is for the red cylinder. I know that the initial potential energy, I know that energy has to be conserved, okay, because there is no friction. So whatever energy is inherent in the cylinder at this location will be the total amount of energy every little step of the way here, the whole entire time, okay? So I can say this then. I can say that the energy at the first point would equal the energy at the second point will equal the energy at the third point, okay? The only energy that's present at the first point is potential energy. Okay, so the potential energy of 1 will equal then the energy that's present at point 2 is all kinetic now. There's no potential because there is no height. Okay, these should be simple concepts at this point. And the potential energy of the third point is then going to be, well, the energy at the third point is all going to be potential. Again, because it's at rest, it came to its highest point and the cylinder is not moving anymore. That being the case, I want to show that the height here at the initial at the initial point is going to equal the height here at the final point. So I don't care about the part in the middle. If A equals B equals C, then I can just say A is equal to C, obviously. So PE1 is equal to PE3. So expanding on the potential energies, we have mass times gravity times height of the first part is equal to the mass times gravity times the height of the third part. I mean, if we look at this, right, the mass of the object didn't change, the gravity didn't change, right? So these two terms I can basically, whoops, backed up one step too far. These two terms I can basically cancel, and I come up with the relationship that H1 should equal H3. I mean, so that proves the point, okay? All right, now we'd have to do the same analysis for the yellow one, except the yellow one we're going to assume that it rolls, okay? So it rolls. There is some friction in the problem then if it is rolling, okay? Because it wouldn't, in order for something to roll, it has to kind of grab onto something, right? Think about your car. When it's driving, the tires have to grip the road in order for the wheel to rotate. Now, this friction we're going to assume doesn't produce any heat though. Now, you know that actually is not the case, right? When you drive your car, after a drive, your tires are hot. Why are they hot? Due to friction. Okay, so this is a simplification, but we have to do it. Otherwise, we can't solve the problem. We don't know enough information. So we will assume that there is friction, but the friction is just basically that that force is kind of translated into then rotational energy. It's not lost due to heat. Okay, so again, that assumption made, the energy at the first part has to equal the energy at the second part, which has to equal energy of the third part. Okay, now this being the case, the only condition that changes is the energy that's present during the second part. Okay, the energy of the first and the third part, the cylinder is at rest in both cases. So therefore there is only potential energy at the first part and the third part. Okay, but the second part now has both kinetic energy of translation, right, or linear kinetic energy, and it will have rotational kinetic energy because the object is rotating. Okay, the first one, the one in red, was not rotating. It was totally frictionless and it was just sliding, no rotation. So that's the only way that these two problems differ. So I would say here that the potential energy of the first point has to equal now both the kinetic energy, I'm just going to write linear kinetic energy, or sub L, all right, plus then the kinetic energy of rotation. And that will then equal the potential energy at the end. Okay, at the third point, and these are both for the second. Now again, if I make that assumption, I mean, this is pretty straightforward, right? Again, I have A is equal to B is equal to C. That means I can say that A is equal to C, and I literally going to do the same analysis. That the potential energy at the first point has to equal the potential energy of the third point. Right, this would be mgh1 is equal to mgh3. I'm writing sloppily because this is pretty, I just did it, right, h3. So there's our final answer. So we just proved them again, okay? So this is all fine and dandy. So that's all for part A. Now part B, let me put it in a different color. So part B, it says find the ratio. Okay, so let's see, find the ratio of the time the rolling cylinder takes to reach the height on the second incline. Okay, so find the ratio of the time the rolling cylinder takes to reach the height on the second incline to the time the sliding cylinder takes to reach the height on the second incline. I think time there might have been a typo here. I think they mean on the first incline, or yeah, I think because they're both second, so we're comparing second to second. So just this should be to the first incline, okay? So basically what we're doing is we're trying to find a ratio between the time it would take the cylinder here in yellow to reach this height versus the time it would take this cylinder to reach its height, okay? Now, here's where the problem becomes a little trickier. Okay, so what we have to somehow do now is we have to somehow solve these equations for time. Okay, basically what I'm looking for is I'm looking for the time, and I'll put this in colors for now. I'm basically looking for the time that it takes for the cylinder to obtain its height, divided then by the time it takes the red cylinder to obtain its height. Okay, now, I don't know why I wrote a 2 there. It should be a T. Okay, so this is what I'm looking for. I'm looking for T over T. Okay, T of the yellow cylinder divided by T of the red cylinder. Okay, from here I'm probably not going to color code things. Well, yeah, I will. Okay, so now how do we find the time it will take? Well, first let's look at this problem from the first point to the second point. Okay. And then if I can understand the problem from the first point to the second point, if I can solve for time, then I know from the second point to the third point, assuming there's symmetry here, right, it would just be double whatever I found from the first to the second, right? If it took 5 minutes to go from 1 to 2, then it'll take another 5 to go from 2 to 3, and the total time would be 10, okay? So I'm only going to look at this, like I said, from part 1 to part 2. So that being the case, I'm going to look, then I'm basically looking at this part of my equation, okay, that I already detailed. So I know that the potential energy of the first point will equal the kinetic energy of linear motion at the second point plus the kinetic energy of rotational motion at the second point. Now let me expand on these terms, okay? This would be mgh1, right? That's the height of the first part. Okay, will then be equal to 1/2 mv squared. And I'll just say this is the velocity at 2. I'm probably just going to leave it as just v now. I could put the 2 in here, but just remember that the velocity here is basically the final velocity or the velocity at point 2. Plus then, and I can basically get rid of this h sub 1. All right, I'm just going to get rid of the 1 there. And then plus then 1/2 now multiplied by the moment of inertia multiplied by the angular velocity squared. Okay, so first thing I realize is that in order for me to solve for time, I have a whole bunch of variables in here. The only one I really know how to get time from is going to be the velocities, right? Here I have a linear velocity, here I have a rotational velocity or an angular velocity. And I would really like to do this problem by finding out the time from the linear velocity, okay? Now that being the case, my thought process now changes from, not changes, but my thought process now becomes, well, how can I need to find a common linear velocity somewhere in this equation, okay? Can I find that somehow? And the question would be, most likely it's going to come through the angular velocity. So I'm now thinking, what's the relationship, mathematical relationship between linear velocity and angular velocity? Oh, right, I remember, right? The formula is this. It's that the linear velocity, aka the tangential velocity. Now, we spoke about this a whole bunch of times. The linear velocity and the tangential velocity of a rotating body are the same, okay? That will equal then the radius of rotation multiplied by the angular velocity. Now, if I were to solve this equation for angular velocity, I would come up with an equation like this, right? That omega is then equal to, I'm just going to write now just velocity. Instead of vt, I'm just going to write velocity divided by r, okay? Now I'm realizing that, oh, look, I can just take this basically and substitute that on in, right, for my omega. So basically what I'm going to do here, since they're equal, I'm just going to take it and plug it in, okay? So now, let's do that. So now here we have mgh is equal to 1/2 mv squared plus 1/2 I times v over r squared. Okay, great. Now, next thing I'm going to look at is I'm going to look at this moment of inertia. Okay, they told us consider 2 cylinders. So here's the formula for the moment of inertia for a cylinder, mr squared over 2. So what I'm going to do is I'm going to expand on this moment of inertia next. Okay, so now the formula becomes mgh is equal to 1/2 mv squared plus now 1/2 mr squared times v squared over r squared. Right, I'm basically just distributing the square. Now notice what happens here. I can cancel the radius, right? They go bye-bye. Now what does that mean? Well, that means that I can now rewrite my formula of mgh is equal to 1/2 mv squared plus 1/2, oops, forgot the 2, right? Don't forget the 2 here. The mr squared is over 2, so don't make a silly mistake. All right, we're all human, so that might happen, but there we go. All right, so the moment of inertia here is mr squared over 2. So this then should be 1/4 now. Okay, multiplied by 1/4 times m, which is the mass, times v squared. Oh my goodness, isn't that quite interesting? Look at these 2 terms, right? They have common, I'll call it a common base. Okay, now I can add those 2 together. Okay, if I add those 2 together, now it becomes mgh is equal to 1/2 plus the quarter is 3/4. 3/4 mv squared. Okay. Now what I'd like to do is let's solve this thing for velocity. Okay. So if we solve it for velocity, essentially we bring the 4 up, right? We just move the 4 up to here. We bring the 3 on down to here. Okay, and so on with the m as well, right? We would bring those just like that and create our little fraction here, okay? I'm just doing it all in one step. And then if I wanted to solve for v, obviously I have to take the square root, okay? So take the square root of both sides, cancel some terms that you might have in common, obviously the masses. And now we have an equation for velocity. Now remember that this is the velocity, and actually I probably should have left in the 2 here, but I just going to get tired of keep writing it. Now remember, this is basically the velocity at point 2, okay? It's going to equal then the square root of 4gh all over 3, okay? Now, this is the velocity at point 2, okay? Meaning at the second point. The velocity at the first point was 0. Now, recall, I have to now somehow figure out how do I substitute in my time value, okay? So remember this formula, and I'm probably going to have to erase some of this work on over here. So remember this formula that the average velocity is equal to distance over time. Now, how do you find an average? Well, you can take 2 values, add them together, assuming there's constant acceleration, which there is, right? Because the acceleration is being caused by gravity. So assuming there's constant acceleration, to find average velocity, you just have to take 2 values and divide it by 2. Okay? So if this velocity here is the velocity at the second point, and I know the velocity at the first point is 0, what's the average between these 2 values? Well, it would be 0 plus this, all divided by 2. Okay? That being the case, I now can write that the average velocity here is going to be over the time, over the period of from frame 1 to frame 2, is going to be radical 4gh all over 3 all over then 2. Okay? Right? Because it's an average. Now, that being the case, this is the time that it will take to go from point 1 to point 2. Now, you can leave it here, but I'm going to find the total time. Okay, to find the total time, remember we talked about that before. All we would have to do here is just then multiply this average velocity by 2. And if we multiply it by 2, notice what happens, the 2's will cancel. Okay, so the total, so the total, let me not do that instead. Hold on one second. So we are going to multiply it by 2, but what I should have done next is really solve for the time now. Okay, what I'm going to do is take this term, d over t, and plug it on in for my velocity, my average velocity. Okay, if I do that now, the formula will become, and what I'm going to do here, one second guys, as you can see the math is nice and long, just get rid of all that. Okay. So now if we were to do that, what formula do we come up with? Well, we come up with now, we have, this is going to get a little messy, but now we would have d over t is equal to this whole thing on the right-hand side. Okay. Now, if we solve that for then t, I know I'm probably losing you at this point. Actually, you know what? Let me just write the work up here. The average, hold on one second. So we have the average velocity is equal to radical 4gh over 3 all over 2. Substitute the d over t on in, so now it's d over t is equal to radical 4gh all over 3 all over 2. Solving this thing for t, okay, we can just, whenever you basically have 2 fractions here, okay? I mean, it's a little complicated because you got fractions kind of within fractions, but if you were to just, let me line this up a little better, you can just move the variables across the equal sign. That's basically what cross multiplication is, right? So just move the t on up here, okay? Move this whole term on down here, and then move the 2 on up there, okay? And that's it. I'm just going to place it. That's how you, I mean, that's how you can do mental math quickly. You just slide the variables on over. So this is now the formula, okay? This is it. That the time is going to equal, well, this is half time, right, though? I'll put a little box, but remember, this is only half time, okay? So this is the time it will take to go from 1 to 2. If I wanted to find then the full time, I would have to take this thing and multiply it by 2, as I was mentioning before. And if I were to multiply it by 2, it would now become 4d, okay? All over radical 4gh over 3 is equal to then t, okay? The full time. All right, so now we have that. So this is really the formula I want. Now, what would we do? we would have to go through the same analysis, but for this, okay, for the red t now. Now the red t is going to be the same formula as this, except there is no rotation. So this whole thing just drops out. It becomes a little easier, okay? So if you want to follow the patterns, let's see if we can identify the patterns. Basically, it would just leave us with this term, right? Solving this for v then, we would get an equation. I'm just going to do it over here. Solving that for v2, right? We would just get, I'm focusing on just this part. Solving that for v2, we would get square root of then 2mg, or actually, because I'll get rid of the m's, 2gh, and that's it, 2gh, okay? Now, 2gh, let me make that square root a little smaller. So this is just square root of 2gh. Remember, this is not the average, okay? This is the velocity at point 2, so we would have to do the same thing we did down here, or I should say over here, to find the average. Now, I would have to divide this thing by 2. Then I would plug in my my d over t, okay? So then I would say that the average velocity is equivalent to d over t is equal to now radical 2gh all over 2. Solve this thing for t, so just start moving the variables across the equal sign. Bada bing, bada boom, here we go. Right, move this on up. I'm basically looking to just get t in the numerator, and that's it. There's your equation, okay? So look, it's basically identical, okay? To this term so far, the only difference comes in the denominator there. That's 4/3, and this is just 2. Okay, why is that the case? Well, because that's the part in yellow was influenced by the moment of inertia. Okay, so now remember, this is half time. So to find full time, just multiply this thing by 2, and we will now get a value of 4d all over radical 2gh is equal to t. Now, what are we asked to find? We're asked to find this, right? T over t. So now I want to take this value. Okay, so let me just... Man, this is all over the place, right? So now let me take this value. Okay, just let me pull it out so I can start erasing some stuff. And I want to divide it by... this thing. Okay. Now we're looking at it and we're saying, oh my God, there's fractions within fractions. I feel like I'm in a dream within a dream. Is this Inception? I don't know. It might be. If you're even still with me at this point, leave a comment below. Inception, great movie. So now, remember, when we are dividing by a fraction, we can do the same thing as multiplying by the reciprocal, okay? So this becomes 4d over... And what I'm going to do here is I'm going to distribute the radical, okay, to every part in there. So this would, and might make the analysis a little easier. So this is now going to be radical 4 times radical, I'm going to keep this together, gh, divided by radical 3, okay? Then times, so now reciprocal of this is going to be radical 2 times then radical gh, all over 4d. Okay, notice what will happen now. The 4d's cancel. Okay, the gh's will cancel. And now we can write what we're left with, and we still have to simplify from here, but we would have now radical 2 all over radical 4. What's radical 4? Obviously that's 2, right? So it's over 2, then divided by radical 3. Now again, I can do the same analysis. Here I have a fraction divided by another fraction. So I can basically just say that this is equivalent to, let me move this over. Don't you love the math? This is equivalent to radical 2 times the reciprocal of that denominator. So times radical 3 over 2. Now here, you have to remember some rules about, exponents and whatnot. I can now alter this to be, this is 2, I mean, if you were to do this in the calculator, that's fine too, but if you want to come out with a fraction, you got to know how to do this. This is 2 to the 1/2, and that's going to be multiplied then by, I was going to say 2 to the 1/2 multiplied by radical 3 all over 2. Now remember, here's you have common bases here of a 2, so you can take the 1/2, this has a power of 1, and you subtract the exponents. So when you subtract the exponents, you would come out to have a value of negative 1/2. So this is 2 to the negative 1/2 now, times radical 3. And the negative just means that you can basically flip this 2. So all this algebra hopefully might be good, but it basically lives in the denominator. That's what it tells us. And then the 1/2 tells us the square root. So overall, this is the answer. Okay. I don't know about you, but I'm getting tired. So that's it. Guys, thank you so very much for tuning in. Okay. Long video, very challenging. Actually, I just noticed letter C explain why the time for the rolling motion is greater than that of the sliding. I just mentioned because of the moment of inertia. I mean, I don't even need to explain it because it was explained in part B, all right, by doing all the work. Guys, thanks very much for tuning in. Please remember to subscribe, tell your friends, help us out, hit the like button. Thank you very much. See you in the next question. Goodbye.